Okay, now this section talks about orthogonality. Now just to give you an idea of what orthogonality means, it has something to do with perpendicular. You know that in 2 dimensions you can define perpendicular vectors, or in 3 dimensions you can define perpendicular vectors. I can kind of draw that here, like these 3 represent perpendicular vectors. This is like the corner of a room or the corner of a cube. It turns out that you can generalize this notion of perpendicular to any number of dimensions. This is one of the wonderful things, that something that's very intuitive and geometrical in 2 and 3 dimensions also works in higher dimensions. Another thing that is coming in this chapter is that we're going to start using complex numbers in earnest. So if you don't remember how to use complex numbers, you should go back and review this section. Important to be able to do, you need to know how to do, you don't need that much to know that much about complex numbers. You need to know how to do complex addition and multiplication, and you also need to know what is a complex conjugate and how to use complex conjugate. That's really all you need to know, these basic operations. You know, hopefully you know that a complex number has this type of form, a plus bi, where a is the real part, b is the imaginary part, and this I is identified as the square root of -1. So I won't say more about that. Go to this section to get more background on complex numbers. But again, you need to know how to add, multiply, and take the complex conjugate of complex numbers. Okay? All right, so we're going to extend this notion of complex conjugate from a number to a vector. And we do that in similar way that we did our previous vector operations. The conjugate of a vector is defined as the vector whose entries are the conjugates of each individual entry. All right, so to take the conjugate of a vector, the ith component is going to be the conjugate of the ith component. And we'll see some examples of this. Hopefully we'll see some examples. All right, so if you didn't give any examples, I'll give an example. So for instance, if I have a vector 1 minus I, 2 plus I, and if I want the conjugate of that vector, well, it's just going to be the conjugate of the first component, 1 plus I, and the conjugate of the second component, 2 minus I. Right, the conjugate just means you change the sign of the imaginary part. Okay. All right, now to get some more properties of conjugation, you have conjugation respects vector addition. What does that mean? It means if I add the conjugate of 2 vectors, if I add the conjugate of one vector to the conjugate of another vector, that's the same thing as adding the 2 vectors first and taking the conjugate. Okay, so you can add first and take the conjugate, or you can take the conjugates first and then add. You get the same result. What does that mean? You don't have to worry about which order you take conjugation in. And this proof is also similar to proofs from the vector section. If I take the ith component of the complex conjugate of x plus y, that's equal to the complex conjugate of the ith component. That's the definition up here. So make sure you understand what this means. This says my vector is complex conjugate of x plus y, and I'm taking the ith component of this vector. That's the same thing as taking the vector x plus y, looking at the ith component, and taking the complex conjugate of the result. Okay. Now from this part, we simply use ordinary complex arithmetic, because x plus y, the ith component, is a complex number. Okay, so so we can simply, or I should say that this is the ith component of the vector, and then you're taking the complex conjugate. So you write this using ordinary vector addition, and then here you're using these are just components, so you're using ordinary conjugation on components. And then this applies this definition up here, and then we get the result that we need. Okay, these are very technical proofs, and if you go into it, there's a lot of detail, but it really is very intuitive. Let me give one example here so you can see what's going on. If I take two vectors, 3 plus 4i, or 3 plus I, and minus 1 minus 2i, if I call that x, and I call y 2 minus I, 7 plus 4i. Now if I take x plus y first, and then take the conjugate of that, that's going to be the conjugate. Well, let's take x plus y. 3 plus I plus 2 minus I. Well, the real part is 3 plus 2 is 5. The imaginary part is I minus I, or 0. So I'll just write that as 5. For the second component, I have minus 1 plus 7 is 6. Minus 2i plus 4i is plus 2i. So this is x plus y. If I take the conjugate of this, that's the same thing as 5. And the conjugate of 5 is just 5 because it has no imaginary part. The conjugate of 6 plus 2a is 6 minus 2i. Okay, so I've taken the sum, then I take the complex conjugate. Now, according to this theorem, I could take the conjugate of x and the conjugate of y. Well, I'll have to do that up here. Sorry. Well, I'll do it down here. So conjugate of x is equal to 3 minus I minus 1 plus 2i. The conjugate of y is equal to 2 plus I, 7 minus 4i. And if you take the sum of these two, conjugate of x plus conjugate of y, so I'm just going to take the direct sum, okay? 3 plus 2 is 5, minus I plus I is 0. On the bottom, minus 1 plus 7 is 6. 2i minus 4i is minus 2i, and lo and behold, I get the same result no matter which way I do it. All right, so that's the only thing that's being stated here. Okay. So we've talked about the relationship between conjugation and addition. We also need to consider the relationship between conjugate and vector scalar multiplication. And it turns out that if you take the conjugate of a scalar multiple of a vector, that's the same thing as first taking the conjugate of the vector, then taking the conjugate of the scalar multiple, multiplying those two together, you get the very same result. Okay, let me do a simple example of that. If I have 3 plus 4i times 7 minus I and 2 plus I, and I take the conjugate of that. Okay. Now, if you do the complex multiplication here, the real part's going to be 21, and then plus 4 gives me 25. That's the real part. The imaginary part is going to be 28 minus 3. So that's minus 20. That's plus 25i. Okay. Then on the bottom, the real part's going to be 6 minus 4, or 2. The imaginary part's going to be 8i plus 3i, so that's plus 11i. Okay. And if I take the complex conjugate of that, I will get 25 minus 25i and 2 minus 11i. All right, so I'm taking the conjugate of the product of two vectors. Now, suppose instead I take the conjugate of 3 plus 4i and multiply that by the conjugate of 7 minus I, 2 plus I. Okay, so I'm taking the conjugates first before I multiply. Well, conjugate of 3 plus 4i is 3 minus 4i. Conjugate of 7 minus I, 2 plus I is just the same as 7 plus I, 2 minus I. Okay, that's kind of sloppy. Let me see if I can do a little better with that. That should be 7 plus I, 2 minus I. Okay, let's do this multiplication now. To get the real part of the first component, I have 3 times 7, or 21. Then I have minus 4i times I, which gives me a plus 4, so that gives me 25, as before. Let's do the imaginary part. Here I have minus 4 times 7 is minus 28. Plus 3 times I gives me 3, so that gives me minus 25I. Okay, looks good so far. That's equal to that. And then for the second part, I'm going to get 3 plus 2, or 6. Then I have minus 4 times minus 1 is 4. Gives me minus. That's going to give me a 2. Then for the imaginary part, I have minus 4 times 2 is minus 8. 3 times minus 1, which is minus 11I. Okay? And notice that these two are equal. So that's all that these things are expressing. They're just expressing some arithmetic relationships. Okay, I'll make this one short, and we'll do each subsection separately.